So, let's go. Number 1. The Lycurgus Cup. Picture a drinking cup sitting on a shelf. In the soft light of a room, it is a cool jade green. Then someone lifts a candle behind it, and the same cup turns the deep red of blood. The glass has not changed. The light has only moved, and yet the color has flipped from green to crimson, as if the object were deciding for itself what it wanted to be. This is the Lycurgus Cup, a Roman cage cup carved in the 4th century of the Common Era, now held in the British Museum, which acquired it in 1958. It is one of the strangest objects ever made by human hands, and for a long time, no one could explain it. The carving on its surface shows King Lycurgus of Thrace, strangled by twisting vines, punished by the god Dionysus for an act of cruelty. But the carving is not the mystery. The mystery is the color. When researchers finally examined the glass under a transmission electron microscope in 1990, they found something almost unbelievable. Scattered through the glass were tiny particles of a gold and silver alloy, each one roughly 70 nanometers across. A nanometer is 1/billionth of a meter. These particles are far smaller than a single wavelength of visible light. The Romans had, without any concept of atoms or particles, seeded their glass with metal at a scale we would today call nanotechnology. The amounts are astonishing in their smallness. The glass contains only about 330 parts per million of silver and about 40 parts per million of gold. These specks interact with light in a way modern physicists describe through plasmonics. Depending on whether light reflects off the cup or passes through it, the particles scatter or absorb different colors, producing the green and the red. In 2013, a researcher named Gang Logan Liu at the University of Illinois pointed out that the cup behaves like a model for modern nanoplasmonic sensors, devices that change color to detect substances. A drinking vessel from 1700 years ago anticipates a tool in a 21st century laboratory. Historians have long resisted this object because it feels too modern for its age. The most likely explanation is humble. A glassmaker in Alexandria or Rome probably added a pinch of precious metal scrap to a batch and discovered a beautiful effect, then learned to repeat it without ever knowing why it worked. They had the recipe, but not the reason. And if a cup could hide nanotechnology, what could be hidden in a small piece of carved Egyptian wood? Number 2. The Saqqara Bird. In 1898, excavators digging in a tomb at Saqqara in Egypt pulled out a small carved bird made of sycamore wood. It was light, only about 39 grams, with a wingspan of roughly 18 centimeters, and it dated to around 200 years before the Common Era in the Ptolemaic period. For decades, it sat quietly in the Egyptian Museum in Cairo, cataloged as one more bird figurine among thousands. Then, in 1969, an Egyptian physician and amateur archaeologist named Dr. Khalil Messia looked at it and saw something else. He saw an aircraft. What caught his eye was the tail. Real birds have horizontal tails that fan out behind them. This carving has a vertical tail fin, standing upright like the rudder of a modern airplane. No living bird has such a feature. Messia also believed the wings showed a slight upward angle, a dihedral, and possibly a curved airfoil shape, the same features that generate lift on a real wing. To him, this was not a statue of a bird. It was a model of a glider. Egyptologists classify the object differently. To them, it is most likely a votive figure, perhaps a falcon representing the god Horus, or possibly a weather vane. They point to the markings of eyes and a beak, which suggest a bird and not a machine. In 2006, an aerodynamics enthusiast named Simon Sanderson built a scaled model and claimed it could generate lift. But aerodynamicists raised a serious objection. The object has no horizontal tail surface, no elevator, which means a glider shaped exactly like this would pitch wildly and could not hold a stable flight. There is also the simple fact that no other model aircraft has ever been found in an Egyptian context, and no Egyptian text describes gliding or powered flight of any kind. Still, the timing tempts the imagination. The Ptolemaic period was centered on Alexandria, a city of remarkable engineering, the same world that would soon produce the inventor Heron. Messia's own brother, a flight engineer, supported the glider reading, and from the 1970s onward, the little bird became a fixture of lost technology literature. The honest position sits between wonder and caution. It may be a sacred bird, a toy, or a weather vane, stylized as Egyptian art, so often stylized birds. Or it may, just possibly, be the trace of an experiment in flight that went nowhere. At least the bird survived. Rome supposedly produced a glass so remarkable that an emperor erased its maker from history. Number 3. Vitrum Flexile. The Romans told a story about a glass that would not break. They called it Vitrum Flexile, flexible glass, and it appears in several ancient sources. The earliest is the Satyricon of Petronius, written in the 1st century of the Common Era, where it surfaces as a dinner party anecdote. The natural historian Pliny the Elder records it around the year 77, and the historian Cassius Dio repeats it in the early 3rd century. The story goes like this. A craftsman gained an audience with the Emperor Tiberius, who reigned from the year 14 to the year 37. The man presented a drinking vessel made of glass. Then, to the horror of the room, he threw it hard onto the stone floor. It did not shatter. Instead, it dented, like a cup of bronze. The craftsman drew out a small hammer and gently tapped the dent back into shape. Tiberius was amazed, and then suspicious. He asked the man whether anyone else knew how to make this glass. The craftsman swore that the secret was his alone. And so, the story says, Tiberius had him executed or his workshop destroyed, reasoning that unbreakable glass would make gold and silver worthless if it ever spread. Even Pliny doubted the tale. He wrote that the story was more widely circulated than well attested, which is an ancient way of saying that people loved to repeat it, but no one could prove it. No physical example of Roman flexible glass has ever been found, which means we cannot test the claim. Modern speculation has wondered whether the Romans stumbled onto something like a boron or lead-doped glass with unusual toughness, the distant ancestor of materials such as borosilicate. The Romans were, after all, brilliant glassmakers. They invented glassblowing in the 1st century before the Common Era, and their workshops could produce glass remarkably thin and strong, which may have seeded an exaggerated legend. The tale also does cultural work. It is a story about tyranny, about a ruler who would rather kill an inventor than allow the world to change. Isidore of Seville repeated it in the 7th century, carrying it into the medieval imagination, and the figure of the murdered inventor, whose secret dies with him, has echoed through history ever since. Whether it was an apocryphal fable, an exaggerated demonstration of unusually tough thin glass, or a genuine lost formula, the glass is gone. But a humble clay jar from Mesopotamia may have hidden something even stranger than unbreakable glass. Number 4. The Baghdad Battery. Around 1936, near the village of Kujut Rabu, just outside Baghdad, a set of unremarkable clay jars came to light. They might have stayed unremarkable, except that the German archaeologist Wilhelm König, then director of the Baghdad Antiquities Administration, looked inside and proposed something electric. In 1938, he published the idea that these jars were batteries. Each one is a terracotta vessel about 13 or 14 centimeters tall. Inside sits a rolled cylinder of copper, and inside that, held apart by an asphalt plug, is a rod of iron. König argued that if you filled the jar with an acidic liquid, such as vinegar or wine, it would behave as a galvanic cell, a battery, generating an electric current. The dating is uncertain, placed either in the Parthian period from 250 before the Common Era to 224 after it, or the later Sasanian period that followed. Reconstructions appeared to support König. In 1940, an American named Willard Gray built a replica, filled it with an acidic solution, and measured a voltage. Later recreations produced somewhere between half a volt and 2 volts. Koenig went further and speculated that the device was used for electroplating, depositing a thin layer of gold onto silver objects. It is a thrilling idea. It is also, most archaeologists now believe, probably wrong. The mainstream explanation is far more ordinary. The jars closely resemble vessels used to store sacred scrolls, sealed at the top with bitumen to protect the papyrus inside. The corrosion on the iron rod, often cited as proof of acid, could just as easily come from organic material decaying over centuries. And there are damning absences. No wires, no conductors, and no linked cells have ever been found, and a real electrical system would need them. No Mesopotamian text mentions electricity or plating, and ancient craftsmen already had reliable ways to gild, such as fire gilding with a mercury amalgam that required no current at all. There is a further frustration. The artifacts were reportedly lost or stolen during the looting of the National Museum of Iraq in 2003, which makes further study nearly impossible. If the jars truly were batteries, they would be an isolated anomaly, a technology with no ancestors and no descendants, appearing once and vanishing. That is the heart of the skeptic's case. Electricity here remains unproven. But just a little to the west, a Greek inventor really did build a machine that spun on nothing but steam. Number 5. Herons Aeolipile. In the 1st century of the Common Era, a Greek engineer named Heron of Alexandria described a device that should not exist for another 16 centuries. He called it the Aeolipile, and he set it down in his work The Pneumatica. The design is elegant and simple. A hollow metal sphere is mounted on 2 pipes above a sealed cauldron of water. When a fire heats the cauldron, steam rises up through the pipes and into the sphere. The steam then escapes through 2 bent nozzles set on opposite sides of the sphere. As the steam jets out, the sphere spins, pushed around by the reaction to the escaping gas. This is the earliest known reaction turbine in history. It is, in bronze and steam, a working demonstration of the principle Isaac Newton would not formally state until roughly 1600 years later, that every action has an equal and opposite reaction. Modern reconstructions of the Aeolipile can spin past 1,500 rotations per minute when the steam pressure is good. An earlier writer, the Roman architect Vitruvius, may have mentioned similar devices a century before Heron, using them to demonstrate the force of moving air. So why did the steam engine not arrive in the ancient world? Why did Heron's spinning sphere remain a curiosity rather than transform civilization? The answer lies in everything that surrounded the invention. Heron treated the Aeolipile as a novelty, a wonder for a temple, not as a source of useful work. Crucially, it had no gearing, no mechanism to convert its spin into labor that could pump water or grind grain. Alexandria, for all its sophistication, lacked the high-pressure boilers and the precision machining that a practical engine would demand. And the Roman economy ran on abundant slave labor, which dulled any pressure to build labor-saving machines. Heron was no isolated dreamer. He designed automatic temple doors that opened when a fire was lit, using heated air to displace water and move a counterweight. He built a coin-operated dispenser for holy water, an ancestor of the vending machine, along with wind-powered organs and programmable automata. The path from Heron to a working industrial engine would not be walked until Thomas Savery in 1698 and Thomas Newcomen in 1712, who succeeded by using pistons and condensation rather than reaction thrust. The gap between Heron's toy and Newcomen's engine is about 1,650 years. Alexandria spun steam for amusement. Far to the east, Han China was using bronze to feel the earth itself shift and tremble. Number 6. Zhang Heng's Seismoscope. In the year 132, a Han Dynasty polymath named Zhang Heng presented the imperial court with an instrument unlike anything the world had seen. Zhang, who lived from 78 to 139, was an astronomer, mathematician, engineer, and poet, and his device was meant to detect earthquakes from far away. It was called the Hufeng Didong Yi, and it was a large bronze vessel, nearly 2 meters across, shaped something like a wine jar. Around its outside were 8 dragon heads, each facing one of the 8 principal directions of the compass. Each dragon held a small bronze ball in its mouth. Beneath each dragon crouched a bronze toad with its mouth open wide. When a distant earthquake sent seismic waves rolling through the ground, an internal mechanism would cause a single dragon, the one facing the direction of the quake, to release its ball. The ball would drop with a loud clang into the mouth of the toad below, announcing both that an earthquake had occurred and which direction it had come from. The exact internal mechanism is still debated, but most researchers believe it used a pendulum, either inverted or suspended, that swung in the direction of the seismic wave and tripped a lever. The device is described in the official Book of Later Han. That same history records a famous episode, around the year 138, when the instrument dropped a ball indicating an earthquake far to the west, near Longqi, some 400 to 500 kilometers away. The court was skeptical, since no one had felt anything. Then, days later, a messenger arrived confirming that an earthquake had indeed struck exactly where the device had pointed. It is important to be precise about what this machine did. It detected the direction of a quake that had already happened. It was a seismoscope, not a predictor, and it gave no measure of magnitude. The original is long lost, and every modern version is an interpretation. A widely reproduced reconstruction by Wang Zhenduo in 1951 used an inverted pendulum but worked poorly. A later reconstruction in 2005, using a suspended pendulum, reportedly responded correctly to simulated seismic waves. Whatever its inner workings, the instrument predates the next comparable European seismoscope by roughly 1,700 years. Zhang also built a water-powered armillary sphere and calculated pi as about 3.162. China learned to sense fire rising from within the earth. To the far west, the Byzantines learned to hurl fire across the surface of the sea. Number 7. Greek fire. Imagine a flame that water cannot quench, a fire that floats on the waves and burns hotter when the sea tries to drown it. This was Greek fire, the secret weapon of the Byzantine Empire, and it was a terror for centuries. It first appears in the historical record around the years 672 to 678, and tradition credits its invention to a man named Callinicos, a Greek-speaking engineer who had fled from Heliopolis in Syria. Its debut was dramatic. It helped the city of Constantinople repel a massive Arab siege between the years 674 and 678. The weapon was delivered through bronze tubes, called siphons, mounted on the prows of ships and along city walls. Under pressure, these siphons sprayed a liquid that burst into flame on contact, and then kept burning even on the surface of the water. Sources insist that water only fed the flames, and that it could be smothered only with sand, vinegar, or urine. The recipe was one of the most closely guarded secrets in the empire, known to only a few families, and to the emperor himself. It was kept so well that the precise formula is genuinely lost to this day. Modern chemists and historians suspect a base of petroleum, of naphtha, perhaps thickened with resins or pine pitch to make it cling and float, and possibly mixed with quicklime or sulfur. The petroleum theory is attractive because the Byzantines had access to crude oil seeping naturally from the ground around the Black Sea, in regions such as Crimea and the Caucasus. To project a heated, pressurized stream of burning liquid would have required sophisticated metalworking and carefully built pumps. The princess and historian Anna Komnene, writing in the 12th century, described tubes shaped like the heads of animals, from whose open jaws the fire roared. Later, smaller handheld versions called chirosophones were developed for closer fighting. Much of the weapon's power was psychological. An enemy sailor faced not just fire, but an unnatural fire, one that defied every instinct about how to put it out. Greek fire helped the Byzantine navy dominate its waters and preserve the empire through siege after siege. Over time, the weapon faded, perhaps as the secret was partly lost, or as enemies learned to keep their distance. The name we use is itself an outsider's term. Western crusaders called it Greek fire, while the Byzantines knew it by other names: liquid fire, Roman fire, and war fire. Whether it was one fixed recipe or a family of evolving formulas, the chemistry of that inextinguishable fire is gone. And to the east, another secret was disappearing. Not a chemistry of fire, but a metallurgy of steel. Number 8. Damascus Steel. For nearly 15 centuries, from around the year 300 to the middle of the 1700s, the smiths of the Near East forged blades that became legendary. They were called Damascus blades, and their surfaces flowed with a watery, rippling pattern, like wind on the surface of a pond frozen into steel. They were prized for a near contradiction. They were hard enough to hold a razor edge, and yet tough enough to resist shattering, a balance that ordinary steel struggles to achieve. The secret began not in Damascus, but in South India and Sri Lanka, where smiths produced a special crucible steel called woots. Woots was made by melting iron with carbon in sealed crucibles, a technique going back more than 2,000 years, and it was traded westward as small cakes or ingots. Smiths in centers such as Damascus then forged these ingots into blades. The watery pattern, called damask, comes from bands of iron carbide, a hard compound called cementite, arranged through the steel. The carbon content was high, around 1.5% or more, well above ordinary steel. And here the story turns strange. The original Indian ores carried trace elements, vanadium, molybdenum, chromium, and manganese, in tiny amounts, and these traces appear to have been essential to forming the banded pattern. In 2006, a team led by Peter Poffler at the University of Dresden examined a 17th century Damascus blade under an electron microscope and reported finding carbon nanotubes and nanowires of cementite inside the metal. These nanostructures, formed entirely by accident, may have helped give the blade its remarkable properties. Then the knowledge died. Sometime around the middle 1700s to the early 1800s, smiths could no longer make true Damascus steel. The most widely accepted explanation is that the specific Indian ore deposits, the ones carrying just the right trace impurities, were exhausted. Without that exact ore, even the same forging methods failed to reproduce the pattern. The precise cycles of heating and forging were also critical and poorly documented, passed by hand and by memory rather than written down. In the 1990s, the metallurgist John Verhoeven and the bladesmith Alfred Pendray spent years reconstructing a plausible Woots process, emphasizing the role of trace vanadium. It is worth knowing that the Damascus steel sold today is usually something different. Pattern-welded steel made by folding and welding layers together to mimic the look. True Woots forms its pattern within a single ingot, through metallurgy, not by welding. The Near East was not alone in mastering such steel. The famous Ulfberht swords, carried by the Vikings between the 9th and 11th centuries, used a related, high-purity crucible steel. Its iron likely traded across long distances from Central Asia or the Near East, centuries before Europe rediscovered crucible steel, making with Benjamin Huntsman in the 1740s. A steel that organized itself at the scale of atoms, forged by feel. And while smiths lost the secret of steel, Rome had already poured a stone that could heal its own wounds. Number 9. Roman self-healing concrete. Walk through the ruins of Rome and you are walking through a paradox. Structures built 2,000 years ago still stand, while concrete poured in the last century is already crumbling. The Romans called their material opus caementicium, and they used it from around the 3rd century before the Common Era to raise the Pantheon, the Colosseum, the aqueducts, and the great harbors. The basic recipe: combined lime, volcanic ash, known as pozzolana, water, and an aggregate of rubble or rock. For marine work, they used pozzolana from sites such as Pozzuoli, near Naples, and mixed it with seawater itself. The results defy expectation. The unreinforced concrete dome of the Pantheon, completed around the year 126, still spans 43.3 meters, the largest of its kind, nearly 1900 years on. Roman harbor walls have survived 2,000 years in seawater, the very environment that destroys modern concrete within mere decades. For a long time, this was a genuine mystery, but recent science has cracked much of it. In 2017, a study led by Marie Jackson at the University of Utah showed that seawater reacts with the volcanic ash in Roman marine concrete to grow new crystals, minerals called aluminous tobermorite and phillipsite, that actually strengthen the material over time. Where seawater corrodes and weakens modern concrete, it reinforced the Roman version. Then, in 2023, a study led by Admir Masick and Linda Seymour at the Massachusetts Institute of Technology turned to small white chunks scattered through Roman concrete, called lime clasts. For centuries, these had been dismissed as evidence of careless mixing. The researchers argued they were the opposite, a deliberate functional feature. They proposed that the Romans used a technique called hot mixing, adding reactive quicklime rather than only slaked lime, which created these lime-rich clasts. When a crack forms and water seeps in, the lime clasts dissolve and then recrystallize as calcium carbonate, filling and sealing the crack from within. In experiments, cracked samples made the Roman way healed themselves within about 2 weeks, while samples without the clasts did not. The Romans achieved this chemistry empirically, without understanding it. The architect Vitruvius, writing in the 1st century before the Common Era, carefully specified the ratios of lime to pozzolana in his work on architecture. Today, engineers study these ancient methods to design more durable and lower carbon concrete, since modern Portland cement, patented in 1824, releases far more carbon dioxide. The Romans built to outlast their empire, but the Greeks built something stranger still, a machine that could calculate the heavens. Number 10. The Antikythera Mechanism. In 1901, sponge divers working off the small Greek island of Antikythera surfaced from a Roman-era shipwreck, lying about 45 meters down, carrying among the cargo a corroded lump of bronze. At first, it was overlooked beside the statues and treasures. It is now considered one of the most astonishing objects ever recovered from the ancient world. The shipwreck dates to roughly 70 to 60 years before the Common Era, and the device itself is generally dated to the 2nd century before the Common Era, around 150 to 100 years before it. The mechanism survives in 82 corroded bronze fragments, but those fragments contain the oldest known geared analog computer in history. Inside this object, no bigger than a small box, were at least 30 interlocking bronze gears. Together they modeled the motions of the sun and the moon and predicted eclipses. A dial on the front showed the position of the sun and moon against the zodiac and the Egyptian calendar. The mechanism tracked the Metonic cycle, the fact that 235 lunar months align almost exactly with 19 years, a tool for reconciling the lunar and solar calendars. A spiral dial tracked the Saros cycle of 223 lunar months, about 18 years, used to predict eclipses. Another dial, its inscriptions read in 2008, tracked the 4-year cycle of the Pan-Hellenic Games, including the Olympics. Most remarkable of all, the device used a pin and slot mechanism to model the varying speed of the moon across the sky, reflecting the lunar theory of the astronomer Hipparchus. The smallest gear teeth are about 1 millimeter across, cut by hand with extraordinary precision. Serious study began with Derek de Solla Price, whose work gears from the Greeks, published in 1974, first mapped the gearing. From 2005, the Antikythera Mechanism research project, including Tony Freeth and Mike Edmonds, used X-ray and computed tomography scanning to reveal thousands of hidden inscriptions, a kind of instruction manual etched into the bronze. In 2021, a team at University College London proposed a complete reconstruction modeling all the planets known to the Greeks on the front face. The deepest implication is this: an object this sophisticated was almost certainly not unique. There must have been a whole tradition of such devices, a lineage of craftsmen now entirely lost. Scholars have linked the device to the school of the astronomer Hipparchus on the island of Rhodes, and to the tradition of Archimedes, who, according to ancient sources, built mechanical spheres that modeled the motions of the planets. Nothing of comparable complexity reappears for over 1,000 years. Step back from the individual objects, and a single thread runs through all 10. In nearly every case, the makers achieved a result without understanding the science beneath it. Roman glassmakers engineered nanoparticles with no concept of an atom. Roman builders engineered self-healing chemistry with no idea of chemistry. Damascus smiths grew nanostructures inside steel by following the behavior of ore and fire by instinct and by feel. This is the recurring pattern of ancient invention. Practical know-how ran far ahead of theoretical knowledge. The craftsmen knew the steps that worked, but not the reasons they worked, and that gap is exactly why so much of this knowledge proved fragile. A principle written down can survive for centuries in a book. But a recipe carried only in the hands of a workshop dies when that workshop closes. This is the difference between knowing how and knowing why, and the ancient world was overflowing with the first kind of knowledge while starving for the second. Many of these inventions also depended on long trade networks. Wootz ingots traveled from India, pozzolana ash from Italian volcanoes, naphtha from oil seeps around the Black Sea. When a trade route broke or an ore deposit ran dry, the technology that depended on it simply vanished. Empires made things worse by hoarding their secrets. Greek fire was restricted to a handful of families precisely so no enemy could copy it, which also meant that one disruption could erase it forever. So when we call these inventions lost, the word usually means undocumented rather than magical. Each one is a case of brilliance without a backup, and that raises a sharper question. If a fragile recipe was the weak point, what were the forces that could destroy such knowledge fastest? Technological knowledge dies in a handful of predictable ways, and these 10 inventions illustrate nearly all of them. The first is resource exhaustion. When the specific Indian ores ran out, the secret of Damascus Steel went with them, no matter how skilled the smith. The second is secrecy. Greek fire and the legendary flexible glass were both restricted to a few keepers, so a single break in the chain could end them. The third is political suppression. Whether or not Tiberius truly executed the maker of flexible glass, the story models a real danger. That power can choose to bury an invention. The fourth is economic disincentive. Herons' steam device had no market in a world powered by cheap labor, so no one developed it. The fifth is misclassification. The lime clasts in Roman concrete were dismissed as flaws for centuries, their function hiding in plain sight. Then there is catastrophe and chance. The Baghdad jars were lost in the looting of 2003. The Antikythera Mechanism survived only because it sank to the seabed and was sealed away from the air. Sometimes function was buried under symbolism. As with the Saqqara Bird, its possible purpose hidden beneath religious meaning. The deepest problem is that knowledge encoded in craft rather than in writing leaves no manual behind. The objects that survive are often accidents, things buried, sunk, or sealed by luck rather than preserved on purpose. Their rediscovery has depended entirely on modern instruments, on electron microscopes and computed tomography scans. For every invention we can name, there were surely others that vanished without leaving a single fragment to argue over. We only debate the lucky few. So how does modern science reconstruct something broken, corroded, or burned almost beyond recognition? The strange truth is that we needed 21st century technology to read the achievements of the ancient world. The nanoparticles in the Lycurgus Cup became visible only under a transmission electron microscope in 1990. The gearing and hidden inscriptions of the Antikythera Mechanism emerged only through X-ray and computed tomography scanning, beginning in 2005. The carbon nanotubes in Damascus Steel were found by electron microscopy in 2006. The crystal chemistry of Roman concrete, the tobermorite growing in seawater, was mapped with spectroscopy and crystallography in 2017, and the lime-classed mechanism was confirmed at the Massachusetts Institute of Technology in 2023 through spectroscopic mapping and laboratory recreation. Alongside these instruments sits the discipline of experimental archaeology, where researchers physically rebuild and test ancient devices. Reconstructions of Zhang's Seismoscope and Herons Aeolipile reveal the steps that the original texts left out, the undocumented craft hidden between the lines. Even the failures teach us something. Wang Zhenduo's 1951 seismoscope worked poorly, which helped later researchers understand what the real mechanism must have required. Modern metallurgists like Verhoeven and Pendre reverse-engineered Woot's steel in the laboratory, and trace element analysis can now pinpoint the lost ore sources that made it possible. What unites all these tools is that they supply the missing why. They give us the declarative knowledge the ancient makers never had. Reading effects the original craftsmen produced by intuition alone. The artifacts become legible only through technology that is itself thousands of years newer than the objects it studies, and the investigation is far from over. Every new scan tends to find more. Yet for all our instruments, some of these recipes still cannot be fully reproduced. It is humbling to admit how much remains beyond our reach. The exact formula of Greek fire is still unknown, never convincingly reproduced. True Woot's Damascus steel has been approximated in the laboratory, but not reliably remade at any industrial scale. Flexible glass cannot even be tested, because not a single example survives. The true purpose of the Baghdad Battery remains unresolved, caught between scroll jar and galvanic cell. The intent behind the Saqqara Bird is genuinely ambiguous, votive figure, or glider model. Even the Antikythera Mechanism, the most studied of them all, has a full gearing scheme that is still partly inferred rather than known. The internal workings of Zhang's seismoscope are reconstructed by educated guesswork, not certainty. And while we now understand Roman concrete, we have not yet matched it for low carbon durability at the scale modern construction demands. Some of these losses are practical rather than theoretical. In several cases, we understand the principle perfectly well, but cannot source the materials, the vanished ores, the particular fuels, the specific skills. Replicating an ancient result can require ingredients that no longer exist, or a craftsman's touch that took a lifetime to learn. The gap between understanding a principle and rebuilding the actual object stubbornly persists. Modern industry, in any case, optimizes for cost and speed, not for structures meant to last 2,000 years. These open problems keep the inventions scientifically alive, not just as history, but as active challenges. And the mysteries that remain are specific and solvable, not supernatural, which leaves one last question. What does this entire list actually tell us about the people of the past? The thread running through all of this is not lost magic. It is lost continuity. The people who made these things were every bit as inventive as we are, working without the theoretical scaffolding that modern science takes for granted. Their genius was empirical, hands-on, and rooted in particular places, particular ores, and particular workshops. That is precisely what made it fragile. Secrecy, dependence on distant trade, and knowledge carried in the hands rather than on the page all conspired to erase what should have endured. When we say that historians refuse to believe these inventions existed, what we really mean is that the evidence looks impossible at first glance. On close inspection, every one of them turns out to be human, explicable, and earned through patient trial and error. The real lesson is quieter and more powerful than any tale of aliens or vanished supercivilizations. Knowledge must be shared and written down to survive. Every surviving artifact is a message from a workshop that no longer exists, and we rebuild their world using tools its makers could never have imagined. This list rewards curiosity over credulity, a sense of wonder anchored firmly in evidence. One day, the future will study our records the way we now study their fragments, and what we choose to write down will decide what survives us. Civilization, in the end, is a relay race of recorded knowledge, each generation handing forward what it has learned. The past was not primitive. It was unfinished business, brilliant and fragile and waiting, across the centuries, to be understood at last.